My project is an investigation of the synthetic image generation algorithm of generative adversarial networks and the technique of feature matching. Generative adversarial networks are some of the most influential techniques in recent machine learning. They have become very popular due to their inventive design and high-quality results. In my project, I have built and experimented with various architectures and flavors of GANs and evaluated them on state-of-the-art metrics. I have also built visualization tools to view the internal layers of the GANs. I have focused on the technique of feature matching, where I also proposed a new method. A generative adversarial network is a model which learns to produce images through the adversarial game of two competing learning agents, a generator and a discriminator. The generator turns samples from a latent distribution into images. The discriminator differentiates between real images and images created by the generator. GANs are the state-of-the-art in image generation and achieve the best results, but they are unstable and very difficult to train. The investigation focuses on 4 architectures, on which 3 are GANs and 1 is a variational autoencoder. The datasets that I have tested on are MNIST, a dataset of handwritten digits, and CIFAR-10, a dataset of real images pertaining to 10 classes. The architecture that I chose to implement my networks in is the architecture first introduced by the deep convolutional GAN. Both generator and discriminator have 4 convolutional layers with batch normalization, with 64 filters in the lowest layer. Here we see some experiments which illustrate how varying the specifications of the deep convolutional networks in the GAN also influences the quality of the samples. On the top row, we see how increasing the depth of the network increases the sample quality. The 5-layer network has quite compelling colors, while the 3-layer network barely converges. On the bottom row, again, increasing the number of features increases quality. The number of features refers to the number of filters in the final layer of the generator, with the second to last layer having 2 times more filters and the one before 4 times more, and so on. It seems that the more filters we have, the more detailed the results are. For subsequent experiments, because of hardware constraints, I have used 4 layers and 64 filters on the final layer. These are all the algorithms compared on the 2 datasets, CIFAR-10 and MNIST. The first notable thing to observe is the stark difference in quality on the CIFAR-10 between the DC GAN and Wasserstein GAN on one side and the boundary equilibrium GAN and variational autoencoder on the other. While the ones on the left are sharp, the ones on the right are blurry. This is because CIFAR-10 is a varied dataset, and algorithms that contain autoencoders seem to perform poorly on such datasets, probably because the approximation of the lower bound becomes increasingly lax with more complex datasets. On the other side, there is little difference between the DC GAN and the Wasserstein GAN. While the Wasserstein GAN is a theoretical improvement on the standard GAN loss, and indeed the Wasserstein GAN sometimes converges more often than the standard GAN, once they converge, the differences seem to fade out, and the sample quality is quite similar. The only particular thing about the Wasserstein GAN visually is that its images appear more edgy than the standard GANs. All GANs seem to perform well on the MNIST dataset, and probably the boundary equilibrium GAN achieves the best results. We can see, however, that neither of the networks produce recognizable and coherent objects in their images. This prompts the need for feature matching, which I subsequently investigated. The next step in my project was to build tools to visualize the internal layers of the GAN in order to see how well each component understands the data. In order to do this, I implemented a dimension reduction algorithm comprised of a principal components analysis followed by a stochastic neighbor embedding in order to represent the multidimensional data in 2 dimensions while preserving the relevant information. I also implemented a deep convolutional classifier in order to label the images generated by the GAN, so that we can trace the activations of the specific classes through the layers of the algorithm. On this slide, we see diagrams of the activations of a deep convolutional GAN when it is generating images from the MNIST dataset. The top left diagram represents an internal generator layer where we can see that the classes are not clearly distinguished. On the bottom left are the actual generated images, so that we can compare the class differentiations there with the ones in the hidden layers. What is interesting is that in the top right image we see how differentiated the classes are in an internal discriminator layer, far more so than with the actual data. This indicates that the discriminator also acts like a feature extractor. On the bottom right we see the same layer in the discriminator activated by the real data, and the class differentiation is almost complete. The differentiation of the classes in the hidden layers of the discriminator is an indication of the difference between the real data and the generated one. To my knowledge, this is the first time such a visualization has been made on the internal layers of the GAN. This gives us an idea. If the differentiation of the class data in the hidden layers of the discriminator is so much clearer for real images than for fake ones, maybe stimulating the generator to produce images whose activations in the discriminator resemble the distribution of the activations of the real data, the object information in the generated images would be clearer. One successful way in which this can be done is to train a denoising autoencoder on the activations of the discriminator when it is fed real images, and then train the generator to minimize the reconstruction loss for the autoencoder when the discriminator is fed generated images. This is called denoising feature matching. Another idea, the one that I had, is to stimulate the generator to perform class differentiation early on in its layers by forcing the distribution of its activations in an early layer to resemble the distributions of the activations in the discriminator. I did this by training another classifier, called F, to differentiate between activations in the discriminator and activations in the generator. Then, I added the negative loss of F to the already existing loss of the generator. It seems, however, that neither denoising feature matching nor my idea seem to improve the generated images notably. This is especially strange, as denoising feature matching is reported to perform significantly better than the standard GAN. The fact that they did not improve the quality in my implementation may be due in part to previously undiscovered instabilities with the DFM technique, and in part with the limited computational budget that I had at my disposal. Here we can see the results of the evaluations. The metrics used, the inception score and the Frechet inception distance, are based on the inception network and roughly measure the quality of the images that the GANs produce. As we can see in the diagram, the best results are achieved by the deep convolutional GAN and by my implementation of feature matching, while the worst results are that of the boundary equilibrium GAN and the variational autoencoder. In conclusion, some general observations are that the GAN, although a very powerful tool, still underperforms in high-level feature processing tasks like object generation, and a reliable solution has yet to be found. The traditional GAN architecture is probably sufficient, and more work needs to be done in compiling datasets that contain more information about the objects. It is also important to explore alternatives to either neural networks or convolutional neural networks. Also, more thorough probabilistic mathematical exploration of the internal workings of the GAN layers must be achieved.